Yes, so the last week we discussed about different types of telescopes and then different techniques that we use in terms of optics that we use to manufacture telescopes. And at the same time, so I talked you that basically there are refractors and reflector telescopes, and we know that from the last lecture that reflector telescopes are more common nowadays. The reason is they can avoid, like, there are few advantages that we talked last time. Because of this, they can avoid this chromatic aberration, and then you can you can get large aperture sizes for a lower price, basically, for reflector telescopes. And also under the reflector telescopes there are different categories like Cassegrain, those kind of prime focus, like that, different types of telescopes. By just although they basically have the reflector method, they, in terms of the technology that they are using, they are slightly different. So that's what we have been actually talking last time. So we talked a little bit about electromagnetic spectrum and the opacity and the limitations of human eye, then the optical telescope types, and different types of telescopes, and advantage of reflector telescopes over refracting telescopes. And then I introduce you few of the world's most popular telescopes these days. So they were this 14-inch largest refractor telescope, and then Keck 1 and 2, like twin telescopes. So these are very large telescopes that astronomers use for research purposes. And this is called Giant Magellanic Telescope, uh, which has 8.4 meter mirrors. And this is called 30-meter telescope and under construction. And the European Southern Observatory 39-meter telescope. And if you were here last time, you know what I mean from 39 meters, right? It's the diameter of this primary mirror of a telescope. Right, so I will start from here today. And there is one important telescope that I would like to talk about. This is actually the future of astronomy research, so that I would think that all of you should know about this. And this is actually a telescope called LSST, or Large Synoptic Survey Telescope. Oh, this is also called as the Rubin Observatory. Rubin is one of the astronomers' name. So this particular observatory uh, is named under his name as a honor for this particular astronomer. And this telescope is in fact a very special one, which will use the highest technology available. And this could be able to do wonders, and let's see the reason for that. And as I have mentioned here, the telescope will produce the deepest and widest image of the universe. So this is one of the things that we will get. And the telescope itself has a 8.4-meter mirror, right? So it's that much large. The diameter of the mirror is 8.4 meters. And so this is basically width of a single tennis court, if you know. And the important thing here is this camera itself. You know that I will explain to you at the end of this particular lecture series. Now these large telescopes, you normally don't use your eye to look at something, right? So what we do is, at the focusing point, we will have a sensor or a CCD camera in most of these telescopes. This powerfulness, or the quality of this CCD camera also decides what kind of things that we can look at. So basically the quality of, or the productivity or the quality of the telescope depends on the CCD camera that you use and the size of the primary mirror. There are other things as well, but these are like two basic things that would decide a quality of a telescope in these research grade observatories. So it's a combination of those two. And this particular camera observatory has this 3200 megapixel camera. Now you could think that the cameras normally we have in our cell phones and all this stuff is like 8 megapixel, 10 megapixel, maybe 20 or maximum 50 or 100 nowadays. But this particular camera has 3200 megapixels in it, and this is a CCD camera. CCD means charge coupled devices, right? There are basically CMOS and CCD cameras. In astronomy, CCDs are very widely used in nowadays, and you will see the advantage of CCDs at the end of this slide. Now, this is in fact the world's largest digital camera now available, right? So, because it's 3200 megapixel camera, and this was now tested and in operation, I guess a few months ago, they started testing this. And this can actually make amazing things. And together with this particular large mirror and the camera, will do all these deepest, widest images of the universe in the next decade. And this particular observatory has not yet started its operation or looking at the sky. And this is, by the way, in the southern hemisphere in a mountain called Chile. And once this is started, uh, this can image size of this will be equal to 40 full moons. Now you can see the size of a full moon, right? And one of these images that this particular camera take is equal to 40 full moon sizes. So it's a very large area that it can take. So that's why uh, this telescope can take very wide images. And this will actually, the plan is to image or observe 37 billion stars and galaxies using this particular telescope during its 10-year survey plan. So this will most probably will start this year, 2021. In fact, this is like a golden year for astronomy, even though we have all these kinds of problems, because we will have this particular telescope starting its operation. And the important thing here is all this data reduction pipeline and everything combined with this particular telescope will make can make alerts that if there is a specific object, it can quickly make an alert so that other astronomers can look at that particular object on the sky, because this will sweep the sky like every night. So the whole I guess within 2 or 3 days it can completely finish observing uh, in the southern hemisphere, the whole sky, scan through the whole sky, right? And for every night, just look at the amount of data that this will produce. It will be uh, 20 terabytes of data per each night. Right? So you can see the amount of data that will coming out. Now, this is one of the reasons that astronomers that who are working in these projects become data science experts, because they are the one actually who basically work with large amount of data in their research. And this will altogether after 10 years, this particular project will collect 10 petabytes of data for doing different kinds of research. So that will be the aim of this particular telescope. Right. Now let's look at a little bit of physics behind these light gathering abilities, how you can calculate those things using some optics equations. You know that as I have pointed out in all these telescopes, the most important part of the telescope is the size of the primary mirror. So it basically decides the light gathering ability of a particular telescope, right? And the amount of light that gathered basically depends on this area of the primary mirror or the lens. I mean, if we are talking about reflector telescopes, then it will be a mirror. If it is a refractor, it will be a lens. But all these large observatories that you have seen in my presentation, almost all of them actually use a reflecting mirrors in their large telescopes, right? Now, this is the equation that you see here is actually the, area of a square. So let me just take this check window out. Now the telescope size is usually given in terms of diameter. So that's what I have this 8.4 meter and all these things. So it is basically the diameter of the primary mirror, and the area is proportional to the square of the diameter. So all of you know that, assuming that is all these mirrors are in circular shape, the area will be 5r squared, right? So if d is the diameter, that will be 5d squared divided by 4. Now this will basically tell you the light gathering ability. Now if you want to compare a 3 meter diameter telescope with a 1 meter diameter telescope, as you can see in this example, 3 meter diameter will take 3 to the power 2 is 9 and 1 to the power 2 is just 1, right? So which means this 3 meter diameter telescope will gather 9 times much light compared to 1 meter diameter telescope, right? Even though it an increase of 2 meters, it will increase the light gathering ability by a 9-fold, right? Because of this square term. Now I expect even in exams that you should be able to do these kind of small calculations, right? If I ask to do it in exam, if I ask to compare light gathering ability of two telescopes, all you need to do is just use this equation to compare it, right? Right, so let's, now this is a nice example that demonstrate what happens when you have a larger mirror and collect more light. Now this is the same picture. On the left hand side, you can see the size of the mirror is smaller, and because of that, you can see that some of the light come from goes outside the mirror. Because of that, in this particular galaxy, this is actually a galaxy, and you can't see very clearly these outside these two parts, which means the outer edges are not that much clear. But if you make it larger, the mirror is larger, and think about the similar situation, then you will get all the light in this whole area into the mirror. And what this would do is actually this whole image can be seen very clearly, and you can see the difference, right, when you have a galaxy like this. So that's why scientists make these larger and larger mirrors, right? So this is just a simple example of that. Right, so let's think about these telescope sizes. And I guess I talked these very briefly last time as well, the smallest size of these smallest professional telescopes, and when you how you go to these large telescopes and so and so. So I will skip this particular slide, right? So I guess this is where I need to start talking. Now another important parameter for a telescope is actually the resolving power of a telescope. Now if you have done a little bit of physics, so I'm not sure whether there are students who haven't done physics in the university. So students who did this probably know about this resolving power. You may even have done some practicals, ask to find the resolving power of a prism or something like that, right? Now larger telescopes are also better to resolve. They are good in resolving two objects, right, that are very close together. So that's something that is needed now for us. When you have very objects closer together, our telescope should be able to resolve those two objects separately, right? Now every telescope that you are using has a fundamental minimum resolution value, right? And this value, we have a specific name, and this is what we called as the diffraction limit. Now students, those who have done some physics, may know that this diffraction limit is normally written as 1.22 times lambda over d, right? You don't have to know any proof or any kind of these things about this, but I want you to remember this equation very well, because this is like a fundamental equation when you are talking about telescopes in our course. And this limit is actually a consequence of the wave-like nature of the light, and basically small diffraction limit make it possible to see very fine details. If the diffraction limit is smaller, that means it is good for you, because you can even look at very fine details. And large in diffraction limit will make the things very blurry, right? Right. Now this is a good example for that. I mean, just from our day-to-day life example. Let's say this is a car or a bus that comes to you. The image in the very left-hand side, image A, you can see that the two lights are separate, right? And when you go a little bit far and far away, you can see that when you go from A to C, the distance increases, and because of that, when you look from your position, those two lights looks like the same, right? So this is, and if you can, I mean, only in the picture A that you can clearly resolve those two lights separate. So this is what in general we mean as a resolving two objects, right? In the picture C, in the right hand side, you can't even resolve those two objects, right? Now this is an example in astronomy what happens for the for different resolving power. You can see the image in the left hand side seems to be a bit blurry, but if you get the same image from a good telescope, you can resolve most of these objects. You can see that objects are well separated, and you can find very fine details are there in the image, right? So this is what happens when you have a good resolving power for a telescope, right? Now this is how in physics actually we determine the resolving power of a telescope. It's basically diffraction limit is what we have to find. Diffraction limit is actually inversely proportional to diameter, and at the same time it is proportional to the wavelength, and you can see that this particular quantity is wavelength dependence in addition to the size of the telescope. Now when you look at these largest telescopes, so their primary period diameter, which is d, is large, and because of that, for a particular given wavelength they will have a small diffraction limit. Small diffraction limit means they can resolve fine details of an object, or even they can resolve two objects that are very close to each other, right? So in addition, so that's the idea here. Now this particular equation right here, I want you to remember this one, right? Diffraction limit, and sometimes we used to write this as theta equal 1.22 lambda over d, as well. This is also correct. In fact, this is actually the exact correct equation, but I mean, as an approximation, we just use the approximation mark here and remove the 1.22 and use this equation as well. But I mean, both are correct, right? This is just to make it easier for you to remember by removing 1.dt, but having 1.22 right here is actually good, and that is also correct, right? So there are basically two properties that we talked about the telescope. And anybody have any questions? Okay, I got a message from someone that he can't see my screen and even can't hear the voice. And this is actually not entirely clear for me why that happens, because I guess everybody else can see the screen, right? You may have to check. You may have to check two things. One is your internet connection, and maybe in your computer some settings may have changed for some reason that uh, probably avoiding you to look at someone else's screen. So that just check why that has happened. I'm not sure why that is happening. Right now, if you need to find a like a diffraction limit of some telescope, let me see whether I can share with you a particular screen. Right, so I guess you can see my telescope. Now once you know this equation d equal 1.22 lambda over d, you can sorry, this is not d, actually this is what you call as the diffraction limit. And what is the unit of this equation, by the way? Unit, this should be a unitless quantity, right? Because lambda is a distance and d is a distance as well, right? Now, for example, if you want to find the diffraction limit of, let's say, Hubble Space Telescope, all you need to do is, first thing is you have to mention in under what wavelength, right? Which wavelength that you are looking at. So if somebody tells you, okay, the Hubble Space Telescope is looking at an object through a filter. So normally filter is something that you, let's say you have a telescope right here, right? And then if you want to use a filter, you have to keep a filter in front of this mirror. So what will happen is when light comes inside like this filter will be filter out all the unwanted uh, light from other wavelengths. For example, let's say you have a red filter here. So if you put a red filter, red has a, assuming that red will have a specific wavelength or wavelength range. So let me assume that red wavelength is between 4000 and let's say 5000 nanometers. Then what happens is when you have this red filter, all the light will once enter to this particular filter, this filter will only allow to go red wavelength, which means all the wavelengths between 4000 and 5000 nanometers inside the telescope, right? And all the other parts of this light will be filtered out. That's what a filter does, right? In case if you don't know. Now, for example, let's say you have a particular filter and the wavelength is given for that is, let's say, 4000 nanometers. Then if this is the Hubble telescope has a primary mirror with a 2.4 meter diameter, and then if you are asked to find the diffraction limit, all you need to do is plug this value of lambda here and then plug the value of d right here. So make sure that you keep the same units, by the way, and then you will get the diffraction limit, right? So that's how you figure it out. And this value will be actually, you have to, this is an angular value, by the way. The value is actually come in terms of radian, which is again a unitless quantity, by the way. Right, so this is just an example how you find the diffraction limit. And I have selected a specific telescope, which is the Hubble Space Telescope here, HST. We used to tell it in a briefer form for a reason. That reason is Let me change my screen sharing to the Microsoft PowerPoint. So first I will stop sharing. Right, so I would assume that all of you can see my PowerPoint presentation again. Now, this equation that I have talked actually valid under ideal conditions. So ideal conditions means that there are this diffraction limited to ability to resolve two objects is actually, this is the theoretical limit. But there are other obstructions when you are observing something from the earth. And this particular issue is actually called atmospheric seeing effect. You probably may not have heard about this before. This is an specific word that we used to use in astronomy. So what this means is actually the most ground-based telescopes, which means the telescopes that are operated from ground. So they are unable to achieve this resolution, theoretical resolution limit given from this equation, right? From the diffraction limits. And this is actually for a reason that when this light rays, so they from an objects in the outer atmosphere, they have to come through the space. No, they have to come through the atmosphere. So once they enter into the atmosphere, because of these different atmospheric effects, the objects become a little bit blurred or not sharp enough, right? And this particular effect, there is a way that astronomers measure this, and that measurement is what we called as atmospheric seeing. And the idea is all the light that is gathered by ground-based telescope first must pass through the Earth's atmosphere. And what happens is actually all the air turbulence in the atmosphere and the refraction. You know that light refracts when it goes to different air columns, because air columns has different density. So one column to the other column, it will always get refracted. So they will go through different paths, right, down through the earth. And then that actually that because of that you will get a blurred image. Now this blurred image has a specific word which we called as the atmospheric seeing. So make sure that you remember this word, right? The reason that I put here is in practice, astronomers usually have this word used very regularly in practice. Now, for example, if you become a researcher in astronomy and go into observing for these large telescopes, what would happen is normally you what happens is normally once you are in the night, you always used to get this measurement. So I will show you how you get this measurement is. So let me just share a different screen and draw a diagram here. So let me have a different. Right, so the way that actually astronomers measure this atmospheric seeing effect is that what actually happens is when you take an image, so you have this large telescope and then you focus a telescope towards, let's say, a star, and then you take an image. So when you take this image, what happens is the light from the star will be focused into a CCD chip or a camera, and then once it gathers all this light, it will transfer all this light into a computer. And there are certain softwares in computers that can open up these astronomical images. Astronomical images actually have a specific extension which we call as FITS images, FITS, and these FITS images can be opened through a certain softwares. And once it is opened through a software, you can actually make a radial profile of those images using another software or a data reduction facility called IREF. Actually, IREF is not widely used now, but this was the primary software that is used by astronomers, I guess, 10 to 15 years ago. Now, what happens is, assume that this is a star, right? Now, you know that when you have a star at the middle point, your brightness is very sharp, or you have a highest intensity at the central point. And then what happens is, if you make a radial profile means if I make it a little bit larger, if this is the radius of the star, and let's say if you are going to measure the light intensity from the center, right? From the center, normally in an ideal star, what happens is in a normal star, what happens is the light get dropped when you go to the outer side, and this curve that when the light get dropped, so we expect this to be I guess it should be a little bit sharper than this. We expect a curve like this, right? Now this is called a Gaussian curve normally in mathematics, and okay, just give me a minute that one of you have an issue here with the encryption or something like that. So just give me a minute to fix. Just to make sure, if there is one student who cannot, he is mentioning that he cannot look at my screen. Is there anyone who has the same problem? Please let me know, right? I'm not sure about this. This could be.
Yeah, the problem persists with the mobile when we open with the mobile phone. The
Yes.
last lectures when I was late for around 10 minutes because of the network issue,
Uh-huh.
and when I was logged in, I couldn't get into the lectures. It was saying that waiting for the host to start the meeting. Or there are some problem when we are using mobile phones for the
Okay.
lectures.
Now here is the thing. The waiting for the host to start the meeting. This actually happens. Just let me pause the recording. So otherwise it will take time for me to just explain these technical things. Right. So what I am trying to explain here is, if there is a light coming from a star that is in round shape, normally we expect a Gaussian curve like this. Now what we normally do is, if you have a good atmosphere, your star, the shape of the Gaussian curve will look like this. Now, let's say you have a windy day, or you have some atmosphere, more turbulences in the atmosphere. What would happen is, for the same star will be look little bit blurred. So it will be something like this. It will be little larger and blurred. Then what happens is, this particular Gaussian curve will expand like that, right? as a measurement of this effect, in an observatory, we used to measure the full width half maximum of this particular Gaussian curve. So what that means is, I assume that you probably know about this. You get the maximum value and then you take the half of the maximum value. Let's say with the maximum value is 500, then you take 250, and then you measure the width of the curve at that particular point. Normally, if you have a good weather on a good day, your full width half max value should be smaller. And if there are more air turbulences and the weather is not good, this value is normally go up to higher values for large. For this one will be full width half max will be larger, right? So that's what we do actually practically as a measurement. And you can, from this measurement, actually you can decide, in if you go for these observatories, they have a rough idea about in a good day, which means if the weather is very good and if there are no turbulences, what would be the value of full width half maximum for that particular telescope. So if then you compare it with that one to check whether your data will be a good or bad on that particular day. I mean, if it goes out of like a large amount, especially this full width half maximum is larger. I mean, if it is very large than expected, then you sometimes even you don't use those data, right? So that's how it works in practical situations. And I mean, for you, just uh, understand that you just what you need is to measure the full width half maximum value of this curve. Normally in an astronomical image is something like this, that you have pixels on the image and each pixel has a value, right? Normally if there is a star, then if it is high intensity is very high at the middle, so the middle pixel has a very large value, let's say 10,000. And when you go into outer region, the pixel values will be lower. And these pixel values, what are the pixel values are what you plot in y-axis, and these are pixel numbers when you go for outer region. So that's what happens in a practical situation, right? I mean, in ideal conditions, actually, you normally assume that the star is like a point source, so that it should be like a point source, and it is the atmosphere who does this distortion and make it bit larger and round shape, right? So let me just stop sharing this and then go back to my presentation to just explain it again. So this is just the practical scenario behind this. And I would assume that you can again see my screen, the presentation, by the way. If you can't see, then let me know. This is just a picture what actually happened. Now you can see that different wavelengths or different colors refract in different ways, so that when it comes to your eyes, they will not in the same phase. So because of that, you will see a little bit blurred image, and the nature of the atmosphere will decide how much or the amount of blurriness, basically. So this is what we called as the atmospheric seeing. As a measurement, what we measure for the atmospheric seeing is that full width half maximum value of a star, right? Right. Now, what contribute to this atmospheric seeing effect? Seeing is actually vary with the location and also vary at a given location over time. So that's basically based on the weather conditions, and it's basically the amount of atmosphere that light has to pass through. Now, this is why actually all the telescopes and all these pictures that you see in my presentations, they are basically on mountains, right? So this is to avoid the atmosphere as much as possible. So when you go into this high altitude or high mountains, you can avoid considerable amount of atmosphere, right? You go a little higher and higher. And when you go for the So that's actually one reason. And at the same time, if you are observing an object, the seeing is actually not that much good close to the horizon. So horizon means, if you know what is horizon, right? Horizon means the, in terms of the latitude, the zero latitude region. So that region, the horizon is actually close to the horizon. Seeing is not that much good, which means there are more blurriness to the image if you are observing something close to the horizon. So what that means is, when you are observing an object, it is always better to observe something when it is very close to the zenith, right? Zenith is the point directly above your sky, above your head actually. And there is something called air mass that you use to measure related to this particular measurement. And this air mass is actually normally close to 1, just above your head, close to the zenith, and air mass will be increased towards the horizon. So when you are going, when you are doing an observation, we also look at this particular quantity called air mass, right? So I will probably include some note about that. I guess I haven't put it here. And we always try to observe something when its air mass is close to 1. So what that means is, when it is close to the zenith, because then you will have good data, right? Good observations and clear images, right? And this is actually a real-time example what happens when you have a good seeing and a bad seeing. Object on the left, image on the left hand side is an image under a very bad seeing value, or there are a lot of atmospheric turbulences, and you can see that you cannot even see the objects clearly. And on the right hand side, you probably have a bit better image. And another effect that goes to the seeing is the temperature. So seeing is worsened by temperature differences between the telescope and the telescope enclosure and the surrounding air. So this is another effect that normally comes into play. That is the temperature difference between the telescope and the surrounding air, right? And because of this, actually we used to cool the mirrors. And I mean, it's not only cooling the mirror is actually also for reduce the noise as well, but basically it's always good to have like same temperature between the telescope enclosure and the surrounding air, so that will reduce the seeing effect, right? Now you can see that there are issues related to these telescopes when you are observing. So this issue is called atmospheric seeing, which is due to these air turbulences. Now astronomers have actually come up with different solutions for this seeing effect. One such, there are three such solutions. Normally we talk in basic astronomy, and one solution which we call as active optics. So this is one method to reduce this effect of seeing from the images. That is actually active optics means make a rapid changes to the tilt of the mirror to compensate for degraded image quality. I said you that there are like different wavelengths come in at different times. Because of that, the image get blurred, right? Now to avoid that, to compensate these differences that happens for these uh, light rays, we can't change that. No, it comes from the atmosphere. So what we used to do is, we get a measurement of that atmospheric effect, and then we deform or tilt the mirror a little bit to compensate for that particular differences coming from the atmosphere, right? And that one way of doing that. And then there is another one called sorry, I guess I told this a bit wrong way. There are two things actually: active optics and adaptive optics. Active optic means you make rapid changes to the tilt of the mirror. So basically try to tilt the mirror a little bit to compensate for these degraded image quality. And the adaptive optics is a new technology that goes a step further. So what we do is, actually in practical situations, we make an artificial star on the sky. So which is that we shine a laser beam towards the sky, which will make an artificial star or a circle on the sky, and then you get the reflected light and then measure the shape of that, and from that you normally get an idea about the atmosphere, right? And then you do a correction or deform the mirrors according to that, right? And this will correct the effect of seeing actually by deforming the mirrors, and this is called adaptive optics. Actually this is now widely used in especially in these professional grade telescopes. I mean, we don't do this for our day-to-day life telescopes because we just looking at the objects just for our own enthusiasm, but for the research purpose we have to do these corrections. And there are certain telescopes now actually use this adaptive optic technique to make these corrections. Now the thing is, you know that atmosphere is changing or very dynamic. It changes continuously. Because of that, you need to make these rapid corrections. I mean, you don't have too much time to do that. And there is another method that we use to tell speckle interferometry, which involves adding up of a sequence of short exposures, each too brief for Earth atmosphere to change significantly. So that is, you uh, make only short exposure images. You take images very quickly and then adapt all these together so that atmosphere does not, you don't give atmosphere much time to make changes and have that effect into your images, right? So those are the three main techniques that we should talk, that astronomers or astronomy instrumentation field that they use to avoid or make corrections for this atmospheric seeing effect, right? So now this section may be completely new for you, so make sure that you go through the presentation and just understand what I have explained here. Right. Now this is an example of improving resolution using adaptive optics, and all of you know that this is Jupiter planet, and on the left hand side is the normal image without doing any corrections using adaptive optics. But if you use adaptive optics and make a correction and take the same image, what you see is the image in the right hand side. Now you can see that the image is bit I mean considerably improved and a lot clear when you use adaptive optics, right? Now, in practice, a way to understand that a particular telescope is using adaptive optics is when you go outside, you will see a nice laser beam shining outside towards the sky from that red, especially red laser beam shining towards the sky from that particular telescope, right? Or from the telescope dome. So that's how you identify they are using adaptive optics. Right. So now by telling all these things up to now, what we have discussed is about these large telescopes and then different issues that we have when we are observing. So one thing that we talked is diffraction limit, how the diffraction limit for effect for the resolving power of a telescope. And then I talked about this atmospheric seeing effect, that is the blurriness of images due to the atmospheric turbulences and different atmospheric conditions. And then I explained to you by few diagrams proving myself that how we measure this atmospheric seeing condition mathematically when you have an astronomical image, and basically it was looking at the full width half maximum value. And then after that we discuss about how to improve this how to improve the telescopes to avoid this atmospheric seeing effect. And then I talked that there are basically three techniques that we use to avoid this effect, that is active optics, adaptive optics, and speckle interferometry. So these are the basic three techniques. And nowadays actually the second one, adaptive optics, is the mostly used technique for ground based telescopes. And this particular image that you see right now in my screen is the improvement made using the adaptive optics for a telescope. Right. Now, everything that we talked up to here, up to this point, is about the telescopes that are on the ground. Right. Now, let's see, you probably have heard that telescopes in space. So there are telescopes in space that you probably know, this Hubble Space Telescope, right? This is very popular. This is like the master in astronomy that is in this space, right? For 30 years now, actually, this was actually roughly started its working in 1990s. Now it's 2020. So for the last 30 years, the Hubble Space Telescope gave us a great service. Now the question that you should have is, even to build this large telescope on the ground, you need to have millions of dollars. I mean, this is a large amount of money, right? I mean, why would you even send these telescopes to space if we can build these on our own telescopes in these mountains? Because I mean, if it has to be sent into the space, it costs even lots of money, right? So there should be a like a justifiable reason for doing this. I mean, sending telescopes to space. Now, Hubble Space Telescope was sent 30 years ago into the space, and this is in fact still the largest telescope in the space. But you will see that in my next slides, the new James Webb Telescope, which is to operate, plan to start its operation from this year, will take the Hubble's place now. But the idea is actually, you should understand now that this Earth's atmosphere causing us a lot of problems, right? And this is why you are measuring this atmospheric seeing and everything. Even though this diffraction limit equation can calculate the diffraction limit of theoretical diffraction limit of a telescope, this atmospheric seeing is actually doing affecting into it, so that the theoretical limit of this diffraction theoretical limit is not the only thing that uh, affect to the quality of the telescope. It is basically the atmospherical seeing for the ground-based telescopes. But when you go for space, what you are basically doing is, actually we are avoiding the atmosphere, right? So you keep the telescope on the space, on an orbit, so that you can avoid the atmosphere. So that's the primary advantage of going into the space. So you get like breathtaking, brilliant images from the space. So this is why Hubble Space Telescope is very popular among astronomers, and even in the public, within the public community, right? Now there are many telescopes in orbiting around the Earth, right? And in some cases even further away. Now these telescopes do not suffer from the effects of seeing, because they are, all of them are in this space, right? Because of that. Now, this Hubble Space Telescope is, in fact, the first telescope to go into space, and this has actually revolutionized. I mean, in this class, first telescope in this class to go into space, and this telescope has revolutionized the astronomy, right? Because of its high resolution images of planets, stars, and galaxies, right? Now, this is an image of the Hubble Space Telescope. You probably have seen this. This is very popular, and you can see the difference from this example, right? This is the same. In the left hand side is the image from a ground-based telescope, which has a which have used adaptive optics techniques to make this atmospheric seeing condition. And the right hand side is the one that is an image taken from the space without any corrections, because you don't need corrections, because you completely avoid the atmosphere, and you can see that how crystal clear in the image when you are taking from the space, right? Now you should understand why people are so concerned putting telescopes in the space. even it costs a lot of money, right? Right. So I will now in terms of telescopes in the space, there are a number of different telescopes now in the space that actually works in different wavelength range, because there are certain wavelength range you cannot even do observations from Earth. For example, X-ray and gamma ray, they don't even come into the Earth, right? So you have to go to space to do the observations. Now, for that, from the after this section, I will talk more about space-based telescopes. There are different types of telescopes under different wavelengths. Now, before that, I want to show you that how astronomers detect all these objects from a telescope and how they store it, right? The normally your normal experience is that, or also you would think that astronomers may be looking at these objects using these large telescopes, using their eye, keeping the eye on the telescope, right? But it is not what actually happens. You only use these small eyepieces and then look at those sky objects in from your naked eye only when you are doing this amateur astronomy. That is just looking at the objects using your own eye, most of the time just for curiosity, right, in day-to-day life. But what researchers actually do is they detect these images and they are going to store it somewhere for their research purposes, right? Now, that's what I have explained in this particular slide. Uh, the light actually has traveled uh, through a telescope, and it can be collected and stored in different ways. Attaching an eyepiece lens allows one to see all of the visible light arriving at the telescope. Now, this is what happens in normal commercial telescopes, that if you buy a telescope from a shop, these are the telescopes that you will get an eyepiece. So all the light is collected and then it will go through an eyepiece, and then you keep your eye on the eyepiece to look at the object. So this is the normal practice. Now this is what we call as the backyard astronomy, which means you can do it from your home. But the problem with the eye is actually eye cannot accumulate light over a long period of time, right? I mean, eye is normally capable of around zero point 0.1 second exposure, not more than that, right? And also the other problem is, you know, that our eye is only sensitive to visible light. We can't look at X-rays, no, or IR or other wavelengths from our eye. So we have to go for other methods. Now those other methods will be, now in maybe I guess 20 to 30 years ago, astronomers used something called photographic film. So these are photographic plates that are placed on the telescope focal plane. So basically you will have a photographic plate placed on this focal plane. So it will, all the light will hit the photographic plate, right? And this is like a photographic plate is a permanent record after that. Then you have to go and look at that. So there are ways to look at the photographic plates. Now, this advantage of this is actually this will allow us to do long exposures, because you can keep the photographic plate there and wait. So this will actually reveal faint light that you cannot see otherwise, right? Because once you gather light from for a long time, then there is enough time even to faint objects, light from the faint objects to come to us and hit into these photographic plates. But actually now we don't use those anymore. So I don't know whether you probably don't have this experience of using these cameras, that you have to use this small reel that you have to go and buy from a shop, and then you have to include it to the camera, and then you will take photographs. Now this is actually what we had when we were in our school time. We did not have digital cameras, so they came later. Now you probably may not have heard about these photographic films. But then after that, in last 20 to 30 years, this technology called digital photography has developed, and astronomers actually use this CCD cameras now. We also call that as charged coupled devices. So that's the long name of CCD. So they are even better because they are very sensitive. They have less noise, and they have a sensitivity for large uh, range of wavelengths, and so they are actually basically very sophisticated digital cameras, right? So they allow us to do very long exposures and get better images. Now the latest addition to that is the camera that you see in this LSST telescope that I have shown to you, the world's largest digital camera. And this is a CCD chip. So you can see that the chip becomes smaller, and at the same time it becomes more sensitive. You can store a lot of light in that, noise is less, and so they are digitally converted, so you can easily store those. So there are a lot of advantage using these CCD chips. And by the way, this charge coupled devices, so the CCD chip is actually works under these mechanisms. Basically, these are actually semiconductor devices, right? If you know a little bit about semiconductors as physics students, and there are FET transistors inside these chips, which is actually not our. It's basically out of our syllabus right now because we are just looking at the CCDs and uses of the CCDs in astronomy. Now, this is the advantage of using these CCD cameras. So they are much more sensitive to faint light than photographic films or plates, and they are also capable of better resolution, wide range of wavelengths, and then digital images are much easier to store and transport. You know those advantages, and they can be analyzed with sophisticated software. And most of modern day astronomy is done using these CCDs, right? Now let me, I don't know whether I may have shown you that image taken from a CCD. Now this is an example like the photographic plates what we had earlier in the left hand side, and you can see that this how CCD has increased the quality. You can see a lot of objects in CCD cameras, right? In this middle one is a CCD, which you can observe a lot of objects from the same exposure time because of the CCD technology, right? So that is that part of the presentation. And for the next one, I will talk about basically some space-based telescopes that are very specific to different wavelengths. Now, for this particular part, let me show you an example. Stop sharing. Let me try to get you an example to show you one of these CCD images. Right, so I'm opening up an example. Let's see what we have here in the documents. Okay. Oh, I guess I have an image here, maybe the Orion Nebula taken from a CCD camera. I may have shown this to you earlier as well, but anyway, it's okay. Let me share this with you. So sharing this. Let me take this. It is still sharing. Okay, right here. Right, so I would assume that you can see the picture that is on my screen. This is actually an image of the Orion Nebula. I don't know whether I have shown this to you. This nice picture is actually taken from one of the telescopes in the Kirkuk National Observatory myself, I guess 3 or 4 years ago, using a red filter. So this basically summarizes everything that I have done up to now about the CCD cameras. Now the advantage here is you use the telescope and this small CCD camera. All the light is gathered into the CCD chip and then it is processed and transferred to the computer. And once it is in the computer, it is saved from an extension called .fits, right? And then there are some specific softwares that we can open up and look at these images and analyze, and then we can look at the pixel values. I don't know whether you will see that in the top left hand corner when I move my mouse across the image, these different pixel values are shown there, right? And also you can change the scale and look at how it works and all kind of things you can do here. You can look at the minimum maximum areas like that, right? So this is just an example of what I have told you up to now, right? So let me stop share this and I will be, so we have some time still left, so I will be sharing the next presentation, which is about different telescopes, right? So let me go into this image. By the way, there are some videos accompanied with these presentations. So I have links posted, and I guess you better go and look at. I mean, there is no point of playing the YouTube video inside this lecture unless it is really needed. So you can, I guess, watch yourself those videos. Just paste the link in the YouTube. You will get some more information about these presentations and details. And by the way, you may get questions even from these YouTube videos, right? Because these are like materials that I have posted. Right, so our discussion on the telescopes now so far has focused on these optical telescopes, right? So that's what we have been doing. Now we are going to switch our study to different wavelengths, how these different, what are the types of telescopes that we have under different wavelengths. Now one such type of telescopes are the radio telescopes to do radio astronomy. So you know that radio waves belongs to a different part of the electromagnetic spectrum, and our eye is not sensitive to radio waves, but still radio waves are there. So there are radio telescopes now the people have built up that we are using to detect radio waves coming out from the space. Remember that I told you visible spectrum is actually a very small part. Visible spectrum is actually a very small part compared to other wavelengths, right? Other wavelengths are actually have more light coming from more waves or more signals coming from other wavelengths. Now, radio waves from space were first detected by this astronomer called Carl Jansky in 1931, and he deduced that this radiation had originated in our galaxy Milky Way. So he is the first one who detected these radio waves from our Milky Way, and this is the beginning of actually the discipline of radio astronomy, right? So that's a different discipline, and there may be some information about in this. Yes, this is. And you probably have heard my sound, this YouTube video. Just go and look at it. This is actually a nice video that just explain this small city in the USA called Green Bank, where they have this one of the largest radio telescopes. Now the Issue with the radio telescope is when you have a radio telescope, you have to ban all other signals coming out for radio signals and cell phone signals and all of those stuff. Now this little village that you have this radio telescope situated, actually these villagers have to get used to it, so they are living without radios, cell phones and telephones, all these things, right? Because they are not allowed to use it in this region, because that will jam the radio signals coming from the outer space for this particular telescope, right? So there are these kind of places, right? And this is the first one who built this large radio telescope, I guess, in a long time ago. You can just read through those things, and these are just history. And this long wavelength radio wavelength basically has a radio waves has a large wavelength, right, compared to visible light, right? Now this will lead to major differences in the telescope design as well. Now radio telescope need to be much larger than optical telescopes. That is because this equation, you can see the resolution is roughly equal to lambda over d. Now the lambda is very large, right? In order to make this diffraction limit smaller, you need to make the d even larger, right? Because otherwise you will have very poor resolution in radio telescopes, because the lambda itself is larger. To make it uh, to make the resolution smaller, you have to make the d, which is the diameter of the telescope, very large, right, compared to the other optical telescopes. Now this is why when you just go and search for radio telescopes normally seems to be very large, right, compared to optical telescopes, right? And they are very sensitive to faint radiation due to their larger size. And this is actually this was considered as the world's largest, one of the world's largest radio telescopes, which called Arecibo. But this telescope actually had a very sad news. Now this is actually collapsed last month. Now the no more longer this telescope is in operation. Now there is a large telescope in China, something very similar to that. That is the larger radio telescope now in operation. This is actually no more in operation. I guess this happened in last month or 2 months ago. Now, compared to the optical telescope, there are some advantages in radio telescopes, because you can do the observations during daytime and even during poor weather, because these large wavelength radio waves doesn't affected by poor weather or whether it doesn't matter whether it is day or time, right? And there are some objects that emit very little optical light, and they can detect quite easily at radio wavelengths. So that another advantage, because there are some objects that emit more radio wavelengths, so you can detect those, and they are not that much affected by the absorption due to the dust. And the other thing is, what we know up to now is the universe actually emits most of its light at longer wavelength rather than optical. And this is why the using radio telescopes are very beneficial for us. Now, to improve the resolution of radio telescopes, a powerful technique that we use in physics is used, which we called as interferometry, right? Now, this has actually allowed astronomers to increase the resolution of the telescopes by a large amount, right? Now, the interferometry actually allows simultaneous observations of object using two or more telescopes. You know that the interference has constructive interference and destructive interference, right? So once you have a constructive interference, that means the signal is coming from different telescopes. If you make a constructive interference, then means the signal uh, become more intense. So that's what these telescopes use. Instead of having one single telescope, they are using a series of telescope to observations, and then they collect all these waveforms to make one signal, right? Now, when you do this, the greater the separation between telescope, better the resolution, right? So this is what physics tells when you look at the interference pattern, right? And the very large array in New Mexico. New Mexico is a state in USA. They actually consist of 27 radio telescopes, and they are spread out over a 30-kilometer distance. So they basically use these series of telescopes for observations in the radio waves using the interferometry. Now this a very long baseline interferometer. So that's another one that uses several radio telescopes on different continents. You can see that when how these technologies are developed and used by astronomers. And this is actually one such example of a radio uh, telescope series. And this is also very popular one, which is in Australia, ALMAO, Atacama Large Millimeter Submillimeter Array. This is also an array of telescopes that they use for observations. And this is an image which you called as neutral hydrogen. Actually, neutral hydrogen wavelength is very important for detecting molecular or very specific reason. And I am not going to talk about this at this particular point because we will be talking about this 21 centimeter wavelength in for star formation lectures. Right. And this is actually another example of advantage of having radio observations. And this orange lobes, we used to tell this as radio lobes, is actually detected by this very large array in New Mexico. If you look at only the other wavelengths, you will not see that, right? So this is why these observations at different wavelengths are important. If you need to get the complete picture, you have to do the observations of the same object in different wavelengths because they will emit different wavelengths at different regions. So you have to combine everything to get the full complete idea about a particular object. Now this is actually a galaxy called NGC 1316, right? Uh, Now, this has been observed by a very large array through the radio telescopes and also from the Chandra X-ray Observatory for X-rays. And there is the story I have written here so that I think I don't want to explain it again. So you can just read through the details. Right. Now let's go into the infrared astronomy. Maybe I will stop here for today. Yes, I just talked continually with you. Now I will talk about three different telescopes that we are using for infrared astronomy. So that's a different range in terms of the wavelength, and this will be probably the, let me see the large, yes, the last section, the infrared astronomy and the James Webb Telescope. And this is the replacement of the Hubble, which will be starting its observation most probably towards the end of this year. And little bit about ultraviolet and X-ray astronomy. And I would finish this next time, and now this will complete actually our first, I would say this is the first part of my lecture series. Then we will talk about our solar system, uh, and different properties of sun and the different planets. So that will be the next section before we move into stars, right? So I will probably start after finishing this section. I will start that particular section on next day as well. Anybody have any questions up to here?